Welcome, everyone. It is my pleasure to welcome you today at the Advanced Computational Science and Engineering Showcase, or ACES. So this event is to highlight the work at Michigan with the goal of catalyzing collaborations and at the intersection of disciplines. So we know that here at U of M, we do a great work in computational science and computer science. And this year's events, we are kind of joining these two topics together. Specifically, we're looking at the intersection between AI, algorithms, computational science, and computer science. We have 6 speakers and panelists that will bring their unique perspective on these different topics. And I just want to wish you a wonderful afternoon and hope this event will spark new collaborations and ideas. And thank you again for coming here. Our first speaker today is Venkat Raman, professor at Aerospace Engineering. So his research focuses on development of computational models for turbulent reacting fluids with application to aircraft and scramjet engines, stationary power generation, and synthesis of novel materials. His research group uses high HPC and detailed numerical simulations to study the performance of combustion devices. His recent focus has been in the areas of numerical error analysis, uncertainty quantification, and failure predictions, aiming towards modeling catastrophic and rare events in complex devices and natural systems. So, welcome, Venkat.
Yes, thanks, Pancho. Thanks for the kind introduction. All right, so I have this is a new set of topics for me. So I have to get used to talking about it. Yeah, so I might be a little bit jumpy initially. So we have a new term which we call persistent computing. And I want to introduce how we think about it and what it means for the computations that we do. So I work in these kinds of topics. We do simulations for aero applications. I'm from Aerospace Engineering, so we do aero applications. And they all use some kind of numerical tools that are discretized on a grid. And so there are a lot of different steps required before you can do a simulation. And after you do a simulation, there are more steps required to interpret them and so on. So these are typically pictures that you get when you run these simulations on a supercomputer. It takes maybe several days, maybe weeks to do some of these calculations. But more recently, we've been critically questioning what it means to do these calculations. And where is time spent when we do CFD? And it turns out over the years, we have managed to compress the time that we take to do the calculations on a computer. And so now, for instance, these simulations will take 2 or 3 days if you use the giant supercomputers that are available to us. But invariably, it takes many months to get to the point where you can run these simulations. And it will take many months after that to interpret the data, to comb through it, and so on. So even though our simulation time is very short, the total time required to analyze these computations is still really large. And as a result, these ideas, this use of CFD, things like this, are becoming very cumbersome to use within a design cycle, for instance, for aero applications, or for that matter, any other use of similar kinds of tools. So there are paths around this. You don't have to do these kind of calculations. You can do what are called multi-fidelity modeling or reduced order models and so on. There are all different flavors of this. But I want to stick with this because these simulations have a purpose and they provide a lot of information. And if you're able to think through them carefully, maybe there's more utility to them than how it's presented right now. And there are things we can do with the new push into machine learning and AI that comes with it. And this is what people have been doing more recently. So for instance, you can do reduced order modeling. You try to compress your simulation so you can run it very fast on smaller number of processors and so But the problem I see there is that when you do this reduced order modeling, you're not really using the full expanse of your compute capability. You're trying to reduce the resources that you want to use so you can do things faster. So it comes with its own limitations and so on. The other opportunity one can have is that there are new hardware, GPUs, maybe other kinds of accelerators and so on. And you can try to see how you can use AI or machine learning to accelerate solvers on these kinds of new hardware, right? So these are all very viable and very interesting paths, and a lot of people at Michigan pursue this and to great success, right? So these are potential paths that are available. But I don't want to focus on this. I want to look at something a little bit different. And we learned this through a sequence of projects we did. And one of them here is from the Defense Threat Reduction Agency. And this is a DoD agency, and they work with, they are the military equivalent of FEMA, okay? And so they have to provide rapid estimates of changing environment, exposure to contaminants, things like that. And so their whole goal is, if, for instance, you have some environment, urban or rural or some other country, you may not know where, and some event happens that spreads contaminants or other kinds of material through the atmosphere, how do you respond to that? How do you evacuate people fast? What should we do in response, and so on? And for them, the time they need to make a decision is very short. They cannot wait 20 hours or 3 weeks to do these decisions. It has to be done in real time, near real time. And so we had this event. I think we all forgot about it. It happened in near the Ohio-Indiana border. There was a train carrying some, really bad, stuff, got into an accident, and it exposed this material in a rural area. So this is that fire from that image. Now, if this happened near Ann Arbor, there's a railway track right here. This could have happened right near Ann Arbor, right? Then we had to figure out, how are we going to evacuate people? We cannot evacuate even the 400,000 in Washtenaw County that fast, right? So we need some strategy to think about what it means in this scenario. So if I knew this event happened and I immediately got on my computer and did CFD, it would take me about 8 hours to get the first result. 8 hours is too long to make any decisions. But you can accelerate it. You can use, different strategies to get to a decision really fast. For instance, we can do this in 15 minutes. Those are all the results that we showed here. You can even compress it even more if you're careful. So maybe like a few minutes, right? So at that point, you now have a new computational framework where you do simulations just in time to be able to figure out what is going to happen. And the way we do this is to think about all the scenarios that's going to happen ahead of time, right? So this is just one-off event. But what we were working on before was bad things happening, let's say, in New York City. So we were given Google Maps of New York City, and we had to figure out if there are different fires or other things happening, how will you evacuate people? So in that case, you just run through thousands and thousands of scenarios. You store all of this information, and when the time comes, you recollect or you take out the information that you need. So instead of doing simulations after the event, you do it ahead of time and store it. So there is a repository, and there's a learning, and so on. Now, of course, New York is just one city. DTRA wanted this for 100 cities around the world, and possibly thousands of places, right? So then the cost of these computations, the ability to store this data, they all explode. And so we had to be cognizant of this. So this is one lesson we learned. So there's a way to accelerate if you can figure out ahead of time how to do this stuff. The second one, this is funded, or but it is funded by Ford. It's now being funded by Ford. And they had a very peculiar problem where they have different divisions within Ford, and one division makes the hood of a car. And then they take the hood, and then they dip it in some solution, and then they paint it. It's electro coating, that's what it's called. But what was happening was the designers were building hoods that will be best for other priorities like safety or how it looks and so on. But when you dip them in the solution, they will bend and they will make the whole hood useless. So they needed a way to assess when they design a hood, is it going to be manufacturable, right? So that's a design constraint. So we could now string together different solution methods, CFD, structural mechanics, image recognition, segmentation, all of this stuff, to create an entire end-to-end framework going from a hood design to predicting whether it's a good design or a bad design, right? And within a fraction of a second, right? That's the goal. And this is what we show here. So you can put together these different components and build this workflow, and I'll say this workflow quite a few times in this talk. And we could build this workflow for this particular problem. Right? So if we know ahead of time what's going to happen, we can, or have some sense of what's going to happen, we can do the computations before. And if we can string together different things, we can create a workflow to go from one end of the question to the other end of the question. So these two are important concepts. So we think that these are critical things that we need to think about. So then comes the use of computation. It's always been unclear to me. I've done CFD for 25 years now. And if you're a professor, you sell what you do as research. And I sell CFD to every person willing to listen. But the problem is it's never convincing. I cannot tell anyone what's the benefit of doing CFD. People already know. They are preconditioned by their training at universities that CFD is good. And so when I say CFD, they go, oh, you are good, right? So there's an association. But I cannot tell what it is. So we have this map. We tried for a long time how to draw this. So on the y-axis there is the cost you incur when you predict something, but you're incorrect about it. So let's say you say my aircraft engine is very good, and you put it on a plane, and the plane crashes, right? So that cost of inaccurate prediction will be in billions of dollars. It will sink the company. Pratt & Whitney 2000 is a good example of an engine that Pratt & Whitney made that almost made the company go bankrupt. Right? So things like this can happen. On the x-axis is how much resource you're willing to put in to make that prediction. Okay? And typically, you cannot put in the same money that you will incur in profit, because then it's not an enterprise anymore. It's a charity, right? So you won't do that. So you need to spend less money to make this prediction, but you should be sure about it. Now, there are certain fields which are agnostic to this, like political polls is a good example. Every year, they're terrible at prediction. So the cost of, they spend a lot of money making the prediction, but they never get anything right. But they come back the next year and do the same thing. So their personal cost incurred in making the wrong prediction is actually zero, right? Nobody drops out of polling just because of this. The other extreme is gambling. You go to a casino, you make an instantaneous judgment, I'm going to bet on 7 or 6 or whatever. So the cost of computing is very low. But then if you make the wrong prediction, you can lose everything you have. So the cost of inaccurate prediction is really large, could be large. In reality, most engineering problems, you will be along the diagonal. So there is a cost you're willing to incur depending on what you're trying to predict. So if you want, like for an Amazon, it suggests what toothbrush you have to buy, right? And it's okay if it's wrong. You just buy another toothbrush. It doesn't change anything. So the cost of making that inference, that prediction, also has to be very low, like much smaller than the revenue you collect. But at the same time, the cost of inaccuracy is also low. At the other end are simulations that we use, like the ones I talked about, like evacuation of people, where if you make an error in judgment, you can lose a lot of people, right? So then you're willing to spend more money on it, but at the same time, you should also be more confident about the prediction. So that puts a limit on what kind of computations you're willing to do for each industry and each application. So this is where I want to introduce this notion of persistent computing. So persistent computing to me is a system, could be a supercomputer, but essentially some kind of AI agent whose only job is to perform simulations and learn from it. It requires no human involvement. It does things by itself, right? We don't want to give it a character, so it does things by itself. And it collects information in a particular way and keeps it. And when the need arises, we go and ask it what we should do, and it tells us this is how you should evacuate people, or this is how you should design this hood, right? So it has a capability to make that prediction. So these are examples that pertain to my own field, which if you now type in ChatGPT 4.0 preview strawberry, whatever it might be, will give you complete nonsense, okay? And we cannot make these decisions based on what it outputs. So we need something more founded on information and data. So we want to substantiate answers with simulation-based data. That's the critical part here. And we also want to be able to remember what we did before. So there has to be a memory to it. So that's definition of persistent computing. But over the years, we have started looking at AI tools as given to us from outside, right? So this is what ChatGPT or Bengio or Hinton tells us we should do, and then we do it, and then we see if it works or not. And we learned a few things from this. And one of the things we learned is that if you take what is given to us as a large language model and you refine it in a particular way for a particular field, it starts being able to say things that are reasonably accurate, that you can start having a dialogue that's not completely unfounded, right? It's like asking any large language model directly. This is an established method, but what we show here is that you can do this for a scientific field, any scientific field, and you'll start narrowing down the hallucinations, the kind of bad responses you would expect. So this is a starting point. This code, by the way, is available online if you guys want to use it. So you can, all you need is a set of papers for your field, you download it, and then it will start going through the data and trying to learn from those syntax how to talk to you about that field. But what we want to go next is to combine that Ford problem, the workflow problem, with this agent. So there exists something that's willing to learn, like the LLM that can add information. Now you have a workflow, which is all the different components needed to go from one end of the decision or the question to the other end, which is the decision, prompt to decision. And this will require use of high-performance computing, all kinds of resources in it. So there are routes to do this, knowledge graphs and other things that you can think about. But much of this goes into grunt work, right? Not everything is like AlphaFold. Some of this is just writing simple codes that will put together the tool. So here, for instance, is a framework for starting from a very fundamental question for us in aerospace to coming up with a code that will execute it. Now it can go on an HPC and then do this. So this is also another piece of software that we had to develop for this program. So if you put all of this together, we get this AI-based workflow, which at some level, that robot-like thing in the middle is the AI agent. It's able to act, which means it can run codes as it sees fit. It has a way to store information, which is our RAG or however repositories are contained. And at the same time, it's able to interact with users in the language that they choose to interact with. This still requires a little bit more definition. There needs to be a specification for how they interact, but that's a different topic altogether. So this whole system can be put together in this sense. So this is what we're working now. So there's the example I showed before is a simple use of some structure that looks like this. So once you have this, you can instrument it with a set of papers or tools or codes and so on, and you'll execute these in rapid succession as resources are available to keep collecting information. And we hope that at some level, it will be able to provide you back information for use in the future. But I want to leave with this. There is a growing sense now, because so far we have been using things that other people develop, large language models that Meta develops or OpenAI develops. But there is a growing sense that these models do not have any sense of intelligence. I mean, people over or exaggerate their capabilities. But just because they talk as if it's a human doesn't mean they can think like a human. So they have to be instrumented with something else, and we do not know what it is. One way to think about it, and this idea comes from Joshua Bengio, who thinks about these things, in my opinion, more carefully than many others, is that these AI models do not have an internal reference. Like when I say I want to do CFD or I look at velocity or things like that, there is a learning, a training that I've undergone that makes me interpret that information. If you just give everything that's there and then train a neural network, it cannot know what the sense of this information is. So he has a way of thinking about it, and our version of this is what I call an AI foundational unit. And this consists of three parts. An AI model, this could be transformers also, although I feel like they are going out of fashion now. We might be going back to RNNs or things in the past because of scaling and resource usage. So we have some model. There is a data repository from all the simulations that have been done in the past and stored in some way. And then it has an internal model of reality. And this is something we specify. And we can instrument anything we want. We can say that the whole world can be fit using parabolic equations. That could be the internal model that we provided. So then the AI model will take the data and try to fit everything to parabolic equations. And then when it gives a result, we can say, oh, you are wrong because you assumed it's a parabola, right? So there is an internal check we can do by probing what its model of reality is. We can also instrument other things. So we can say, for instance, every aircraft engine will have a compressor and a combustor. We can say things like this. And so when it collects information, it will know how to segment it, how to put it in different parts, and learn from it. And this model of reality doesn't have to be constant. Other AI agents will have other models of reality, and so they can compete with each other to figure out who gives a better representation of the outside world. And so some will win and some will lose. So there's a game theory on top of this to figure out which foundational units will win. So there's a whole field that can be built around just this concept, right? So the persistent computing is the start of this. So we need to be able to instrument these agents to be able to do simulations on their own. And now if you give this foundational unit access to a supercomputer, then we can figure out what is it that they actually learn. Okay, this is all I have. Thanks.
Questions?
So if I could, so suppose I was in an agent which is trying to do bad things. So if I steal your model, I can use your model to help me figure out what's going to be most destructive.
Yeah.
Okay, so you're going to have to make sure nobody steals your model.
You cannot ensure that.
Yeah.
You cannot ensure that. So, this is the problem with abstraction, right? If you can abstract any information, somebody will steal it. So you can live off of complexity, which is the DoD, path to defending this country, is to make things supremely complicated that nobody can figure out. Yeah.
Actually, I've seen the Army try to simulate using cellular automata. What happens if somebody sets off, say, a bomb, let's say a gas bomb.
That's right.
And they blow up bridges, so you can't get out.
Yeah.
And so the Army was trying to simulate that. Well, that wouldn't be in your system necessarily, but they would, in fact, they could test your system and see, could you handle that?
Which is why you need to have an internal model for the AI agent. You have to tell it what is possible, right? And then when you think of this, you can tell it, look, what you had before was not right. All the bridges could be blown up. Now figure out what to do. And then, so that interaction, that updating of models should be there. Yeah. And if the other side figures out a better internal reality model, then it's game over. Yeah. So that is also there. Yeah.
Yeah, so you show one slide, there is a comparison between the CFD simulation that took 8 hours and the machine learning prediction take 15 minutes. My question to you is, if you use a machine learning prediction, how can you guarantee, so if you encounter uncommon boundary condition, so how can you guarantee?
Which is the same question as before. If you haven't seen it before, then what are you going to do, right? Which is why the internal model matters. So the internal model will allow you to extrapolate, which machine learning will not allow you to do. So I have to know if I go in a straight line, if I keep going, what will happen, right? For that, I need to know there's a straight line. So just giving data points to learn will not work.
So when you say the internal model, you mean the internal model of your CFD simulation?
It's, I think in this context, it'll be different, right? In this context, it'll be, let's say I know for this particular region, if this is the type of event I want to capture, right? What is the main input here is the weather prediction, the wind information. So that is the boundary condition. So I can say in Ohio, over the last 50 years, every month, what is the spread in wind direction? So that will be my boundary condition. That will be my internal reality model. Now, if climate change changes that, then it's no longer valid. Yeah, so I have to update for that. Okay, all right.
Well, just in 4 minutes. So,
Okay,
so,
not so fast.
yeah.
Literally stays on time. Like it's usually the other way around, you know? So, yeah.
So, so I think a lot of these things, help get us some information about the problem. Right? But generally, at least in many applications, people require high fidelity answers at a much deeper level than what some of these newer tools can give. And I think you already touched upon it. The internal models you have are also certainly not perfect.
Yes.
And that's all. In many cases, that's a stumbling block. It's almost like, I don't know, the cliche that goes, you can automate 90% of it, but the other 10% will still be a bottleneck.
That's right.
So I guess one of your ideas is when the computer is not asked to do something, it is going and building better internal models. Is that the idea?
So I want to believe, at least initially, that we are the ones who provide the internal model. Yeah. I think there's a lot of danger in just saying whatever internal model it figures out, it will do it, right? And by providing the internal model, we're also saying these are the rules of the game. And I can come up with a lot of social examples where individuals can give the bad internal model.
Let's stick to science examples.
But it's I think it's somewhere we have to have an input. It cannot just unbounded search for things. There's no possibility.
Yeah.
So you need to constrain it somehow. And the internal model is a constraint.
All the knowledge and the resources and everything we have to persistently build that internal model.
See, for instance, if I show many pictures of gas turbines, aircraft engines, right? It may not know how to interpret it. But now if I say, look for where you have a lot of temperature, high temperature, look where the speed of the flow is very high, things like that. It will now start segmenting that image to say, oh, this looks like one unit, right? So my internal model can give that information again and say, look, there are 4 parts. Go to every image and figure out what are these 4 parts. Something like that. Yeah. Okay. If you're exact. There's 30 seconds left. There's 32 seconds left, I think. That's, yeah.
Go ahead.
So if the internal model is not well established, or if I don't have a good understanding of the reality, maybe maybe it's because it's integrated parts, so I don't know the behavior of that system. I should not use this workflow to explore new designs. I can only do fine-tuning.
So somehow the internal model should be readable to us, right? So then you can look at the internal model and go, this AI will know nothing about, making cookies, right? So I need to be able to say, what is that agent capable of knowing? And then the AI model only provides answers for that universe that it has learned things in. And that's what the internal model is.
So if I don't know, the AI won't know because it won't be able to explore.
Not right now. Yeah, that's right. I do not. Yeah, I want to keep it that way. Yeah. You can
answer questions later.
Thank you
We
very
want to
much.
thank
Thanks, guys.